Hi, my name is Gary Lloydhäuser, and I'm going to be talking about the concept of multidimensional divide and conquer. This is an algorithmic paradigm that's both general and specific. And so it's general in the sense that it applies to a wide range of problems that share similar characteristics. And it's also specific enough that it provides a pretty well-defined strategy for dealing with problems of those aforementioned characteristics. So, what is multidimensional divide and conquer? Let's start at the highest level possible here. So, simply put, multidimensional divide and conquer is a technique in which you solve a problem of size n, in k dimensions by recursively solving two problems of size half of n in k dimensions, as well as one problem of size n in k minus 1 dimensions. And this diagram here is color-coded to the text to sort of demonstrate that idea. If you have a problem of size n in, say, 2 dimensions, which is represented by these two boxes here, and you want to solve it via multidimensional divide and conquer, the overall strategy is that you will first divide it into two problems of half the size in the same number of dimensions. And then you'll perform this marriage step out here, where you reduce the dimensionality by 1 and recover the initial problem size n all the way back to n. So that was the basic structure for just 2 dimensions there to sort of get the feet wet. And let's advance that on to actually be in 3 and more dimensions. So here we've represented, here's the first 3 dimensions of n, and then you have an arbitrary number more, and we might call this total number of dimensions k, where k is greater than 2. So the first half is the division part of the divide and conquer, and that involves maintaining the same dimensions, but splitting into problems that are half the size of each original problem. So we start with n, we go to n over 2 in the first layer. In the next layer, we split to n over 4, and we continue to do this until we've hit our base case, which in this case I have represented this by having a problem size of 1. So it's also important to note that, yes, this would become a little more complicated if n is not a power of 2, because it wouldn't nicely divide into these problems of size 1. But for the sake of simplicity, during this initial discussion of multidimensional divide and conquer, we're going to keep it a little bit simpler and say that n is a power of 2, so that it will nicely divide into these problems of size 1. Now once you've done that, you can start to solve these very simple little base cases and recombine them. And the recombination is somewhat interesting because you actually, knowing the information that you know from solving these problems of 1 point in k dimensions, you can actually project onto one of the other dimensions as you go, and therefore eliminate a variable and a dimension with each step of the marriage. So you can see here we take these two solutions to these problem sizes of 1 in k dimensions and combine them to form a solution of size 2 in k minus 1 dimensions. And you can continue doing this in the same fashion as that beginning, to sort of take these two and combine them into this solution, and so on and so forth, until you've obtained your total solution, which is an operation on n items in one-dimensional space. So now that we've kind of talked about the overall idea of multidimensional divide and conquer, what can we do with it? Where is this idea useful? What kind of problems can we apply it to? These are all questions that naturally come up now that we've studied it. And one of the first problems is that of some statistical measures of the data. And in order to get to this problem, we're going to start with a little bit of background. And that background is called point domination, right there. So what does it mean for a point to dominate another point? Well, we can see here we've got a bit of a formal definition. A point x dominates a point y if and only if x's value is greater than y's value in every dimension. So to demonstrate this, I've mocked up a simple diagram in 2 dimensions. Your first dimension being this way and second being that way. It's easy to visually grasp physically. And you can see that, let's start with point 1. Point 1's value in x is less than every other point. You can tell because it's the furthest point to the left. Point 1's value in dimension 2 is also less than every other point because it's beneath every other point, so to speak. So in this way, we can move on to the next point and say, well, point 2 is certainly to the right of 1, and it's certainly above 1, so therefore point 2 dominates point 1, because in dimension 1, it's greater value, in dimension 2, it's greater value, and that's what this red line is here. So you have the dimension 1, dimension 2. And likewise, you can see for point 3 dominating point 1, but point 3 does not dominate point 2, and this is important to remember and to notice, because point 3 actually only dominates point 2. Well, I shouldn't say it dominates, but rather it's only greater than point 2 in dimension 2, which is this dimension here. But it's actually behind 2, to the left of 2 in dimension 1, making it less than 2 in dimension 1, and therefore it does not dominate. It's an all or nothing sort of characteristic of 2 points, or of 1 point over another point. You can't exceed it in only 1 dimension, it must be both. So in 2 dimensions, you can sort of think of it as a to the right and above rule. Point 4 is the king in this example, because point 4 exceeds the other 3 points in both dimensions. So now that we've kind of got the idea of domination down, we can move on to rank. And rank is a pretty simple extension and use of domination, if you would. The rank of a point P is equal to the number of points that P dominates. It's quite simple. So the rank of 1, point 1 here, is 0 because it doesn't dominate any points. The rank of point 2 is 1. And we can see the red line here representing the 1 point that point 2 dominates. And likewise, the rank of 3 is 1, and the rank of 4 is actually 3 because it dominates these 3 points here. So with that in hand, we can advance on to building up our actual problem, which is to find the empirical cumulative distribution function, which I'm going to refer to as the ECDF of a given set of points S. And so let's talk about it a little bit formally. So for a set S of n elements, such as this one here, this is a set of 4 points. The ECDF of S, S being this, evaluated at x, where x is a specific particular point of S, so one of these 4 in particular, is the rank of that point, x, divided by the total number of points in that set. So we can come down here, and we can sort of see the box that's here to extend this, where the ECDF of 1 is 0, because the rank of point 1 is actually 0, and 0 divided by, any other number is going to result in a 0 there. And likewise, you simply take your rank of those points and divide them by the total number of points, and you can come up with your ECDF numbers. So why is this an interesting problem? I mean, at this point, if you're unfamiliar with these problems, you might say, well, now we're just making things up. This ECDF doesn't sound very useful. It's almost too simplistic to be useful. But you can rest assured that if you're curious, it is commonly used in statistics to estimate the distribution of a set if you only want to look at a subset of its elements. Maybe only a subset is available, or maybe for performance reasons, you only have time to look at a subset, and an estimation of the underlying distribution is good enough. So that being said, there's a couple of variants that we can examine with regards to ECDF. That's, first of all, the all points problem. And the all points ECDF problem says for a given set S of n points, I would like to know the ECDF of every individual point. So we've actually conducted an all points here on these 4 points. We've conducted the all points by giving the ECDF of each of its points. There's also the searching problem, and this is a little bit different. This says, given a set of points that we know we have our hands on, we can kind of grasp ahead of time, can we produce some data structure or some prepared way of quickly answering the following question, which is, if we take a new arbitrary point, maybe the point exists here where the laser pointer is, we'd like to quickly report the rank of that new point, or I'm sorry, the ECDF of that new point with respect to the rest of the points in the set. And obviously recalculating the rank of that point with respect to these points is going to take a lot of time, and perhaps we can do a little bit better than that, better than just brute forcing it. So those are 2 ways that we can discuss the ECDF that'll come up as we move along here. So that being in mind, let's have a quick little review of what we've worked up to so far. So we started off with multidimensional divide and conquer, which if it were on the slide, it would be somewhere over here, completely disconnected from the problem that we've built up contained within this box. And you can see here we started with sort of a implicit understanding of point. That's why this is sort of translucent, because I haven't explained what a point is. It's simply assumed that we can agree on the meaning of a point in some number of dimensions. And with that being said, we can then define what it means for one point to dominate another point. And I've done that in just these previous slides. On top of that, we then took domination and said, well, how many points does a given point dominate? It's a very simple extension, and we've established the idea of rank in that manner. And finally, using rank, we've built up to this overarching idea and our problem statement, which is, let's talk about calculating the ECDF. So in this way, we've sort of established this hierarchy of understanding. And hopefully this quick review diagram helps you mentally sort of organize the information that I've presented to you so far, so you can keep it in line as we move forward into providing an actual solution using multidimensional divide and conquer to these problems. So a little bit more specifically about the all points ECDF problem. To reiterate that, it involves calculating the ECDF at every point in a set of points, as we sort of established before. And let's talk about the roadmap that we're going to take to actually work up a multi-dimensional divide and conquer solution. So you can have kind of a reasonable idea of why we're doing what we're doing while we're doing it, and sort of have an overall idea of where we're headed to sort of help you fit each step into a higher understanding of our overall goal. So this diagram here sort of represents the roadmap, so to speak, and it's sort of, perhaps organizationally intelligent to have this sort of hierarchy where we build up our solution one dimension at a time. And the reason for that is that multidimensional divide and conquer, as well as the ECDF problem, can exist in large numbers of dimensions. But especially because it's recursive, we want to be able to have some sort of base cases, and sort of maybe it'll help us understand the higher dimension solutions and the general pattern if we start with simpler situations. So we'll be starting off in one dimension, represented by this line. These are sort of physical examples because I think that sort of is easy for me to understand and grasp physically. We'll move on to 2 dimensions. I represented here with a square. 3 dimensions with this cube here. And then it sort of falls apart after that point. This one's supposed to represent k dimensions, arbitrary dimensions, because I don't know necessarily a great physical way of representing something like that. There's no physical object I can sort of put there that easily represents an arbitrary number of dimensions. But one way to visualize it, at least purely mentally, is to consider perhaps data about cars. And if each point on a set of 4 dimensions represents a car, a given car, then the first dimension might be its top speed. The second dimension might be the color of the car. The third dimension or characteristic could be the materials the car is made out of, and the fourth dimension might be its use or its purpose as like a race car or a transportation of goods like a truck or a semi truck or something like that, or maybe it's just a regular car for general purposes. But that would give you 4 dimensions that I can't necessarily easily represent physically as a physical object, such as the physical dimensions like I've done with the other ones. But I think it works nonetheless. So that being said, we've sort of established the roadmap that we're going to go up by dimension. So that naturally says, well, let's start with the 1 dimension all points ECDF problem. And you'll be pleased to find that this one is not too hard to solve, which is going to be handy as we go forward. So what's our input to this all points ECDF in 1 dimension problem? Well, it's a set of S, and we're going to call that, it's a set of points, and we're going to call that set of points S. And that set of points must exist in only 1 dimension. That's our restriction. That's our assumption. So here's an example set of points. We've got the point 1, 6, 16, 10, 4, 14, 20. Pretty much just random points. And our output is going to be the rank of each point in S. And you might be saying at this point, why are we outputting the rank? The ECDF is not the same thing as the rank. And I'm just going to make this quick note. It's just for simplicity's sake. As it says down here, rank is just 1 division away from ECDF. Here, there's 7 points. All we need to do is divide the rank by 7 to get our actual ECDF. So for the most part, rank and ECDF are close enough to where, let's just discuss rank. It's easy enough to simply add that division in if and when you want to accurately implement ECDF. But it can kind of reduce the mental clutter we have to deal with as we explore these ideas. So what's our solution? Well, we can just sort the numbers, right? There's only one comparison that needs to be done, and that's the relative value in our single dimension. In order for a point to dominate in 1 dimension, it only must be greater than any other point in that 1 dimension. And conveniently enough here, the index of each number, if you're 0 indexed, actually directly gives you the number of points that point dominates. So in this case, we've sorted our set S, and the sorted representation is here, along with the index. And you can see that sure enough, if you arrange these points on a line, this point is to the right of 1 point. This point's to the right of 2, and you can see that right there, and so on and so forth. So what did we have to do? All we had to do was sort the numbers, and we can retrieve anything. Well, we can retrieve the result we want whenever we would want to retrieve it. And this requires the optimal sorting time, which is commonly known to be n times log n time, where n is the number of elements in S. So that's a great runtime. It's a very efficient solution for 1 dimension. So building on that, let's see if we can't sort out performing the all points ECDF in 2 dimensions. Then we'll step it up 1 dimension from the previous solution. So again, let's discuss our input. It's going to be a set S of points again, but each point has 2 pieces of data. Its value in dimension A and its value in dimension B. And I've just simply arranged this as, the curly braces for a set, and then each one is just a 2-tuple, where the first value is maybe its is here its value in A, and the second value is its value in B. So for example, this point 5, 20 is located right here. And I'll move my laser pointer so you can actually see it. But that is that point. And maybe 9, 6 is here, so on and so forth. So let's revisit how multidimensional divide and conquer is proposed to work. So we want to recursively solve two problems of half the size in the same space, and one problem of the original size in one less dimension. Now, the reason that I've highlighted this green here is because if you recall, we've actually already solved the one-dimensional ECDF all points problem. That was what we did before, and that's why it makes sense to sort of build our solution up from lower dimensions, because as you divide your problem into smaller subproblems, and as you take away dimensions, you're relying on your ability to solve the problem in those smaller dimensions, particularly our base case of one dimension. So this problem is solved. So essentially all I'm trying to say is if we can reduce our problem to this, then we've done well because we know how to solve that problem. So here's our data set again from the previous slide. And the way that we're going to try and solve this problem is we're going to make a dividing line such that half the points lie on the left of the line and half the points lie on the right. And again, just to reiterate, this can get a bit nastier if the number of points is not a power of 2. And, you know, if, say, it wasn't divisible by 2, even more strictly in this case, or more generally in this case, then we might not be able to make this dividing line neatly divide into two groups. But for now, we're just going to assume that, sure, the number of points is actually a power of 2, which gives us these nice properties. And the rest of the details can be worked out as needed, but don't necessarily need to be addressed here, as we're just going for an overall understanding. So we're going to continue doing this division, because as you might recall, multidimensional divide and conquer states that the way we're going to solve problems is we're going to recursively solve the two subproblems that we create at each step. So these are the two halves from before, that the blue line that we wrote before divided us into half, the left half and a right half again. Now we can draw another line for each of those, and they'll again split. So we've basically split our problem of 8 points at this point into 4 problems of 2 points each. Now that we've done that, we're rapidly approaching our base case at this point. Obviously, if we had more than 8 points, we would continue to do this until we partitioned into lone points, but in this case, we've already reached that stage. And you can see when we draw this final purple line here, this is just one of those previous 4 partitions picked at random for the sake of demonstrating it. When we draw this final line, we end up with just one point, in each partition. And we have a very interesting observation that we can make at this point, and certainly we could have made this observation earlier, but we'll go ahead and make it now, is that no point on the left side, let's say in the left partition, when we draw a line at any point, any of those previous diagrams, this holds true for, a point on this side of the line can't dominate a point on this side. And then further, a point on this side can only dominate a point on the left side if it's greater than the point on the left side in all other dimensions other than in all those dimensions which we've used to divide our partitions. So in this case it's 2D. We've used the dividing line is in the y dimension, and we only need a line. So that's our criterion for domination, is this point would need to have a higher y value than this point in order to dominate it, and that's very clear. So we can solve this problem at this point. We know how to do that. The rank of the point by itself is 0. Or, I'm sorry, once you get down to 2 points, the rank of the point in the left side is 0 because it can't dominate the one other point that's in the partition. And the point on the right side, we can simply check if its y value is greater than the point on the left side. And we can do this by projecting these values onto the y-axis and also keeping track of whether it was on the left or the right of the dividing line. So here we have the 2 points. 520 is this point, and it's on the left side, so we just created a little object and attached that data to it. And the next point is 6, 8, and it's on the right side. We've maintained that information. Now we're gonna sort by the y value. And from this point on, we don't care about the x value. And the reason for that is we've sort of performed that implicit projection where we already know that points on the left can't dominate points on the right. And we only know that because we know the relative x values of the 2 points, where we imply that by using the words like left and right. So essentially, this is where we've reduced the dimension of the problem by 1, is when we perform this implicit projection. And so we're going to sort by y value the 2 points we have here. And we end up swapping the 2 values in this case. And at that point, we can perform our scan and see if the point on the right is actually greater in y value than the point on the left. And we can do this by maintaining simply an a count variable. And as we scan these values, a count is incremented every time we see something that's from the left side of the line. So for example, in this case, our first step of scanning is we hit this 6, 8 that we know is from the right partition. And we know that the rank at that point is equal to the number of points on the left that it dominated. Well, that's equal to the number of points on the left we've seen so far, since they're arranged by y value, which is 0. Then we'll continue our scan. We'll hit the next point, which is from the left. We already know the rank is 0 for this point, because there's only 2 points. This is the base case. But what we need to do is update our a count, because we've seen a point from the left. So we can update our a count, and it becomes 1. We just increment it for this. So, supposing there was a third point, which there isn't, that was from the right side, that third point would then have a rank of at least 1, because it dominates at least this point. So in this way, we can take each of our splits that we made before, that have only 2 data points in them, and compute our local ranks using the method that we just discussed. And they're fairly straightforward, even disregarding that method. The method will become more useful as we perform marriages of these sets to each other. But you can of course verify that these values look as you expect, that the point on the right is lower, so it's 0, and the points that are on the right and higher have a rank of 1 with respect to these local groupings. Of course, the rank of this point may or may not actually be 1 once all the merging is complete, but these are just local ranks. Now, as we move forward, you can see that we've combined the 2 diagrams that were previously on the left and the 2 diagrams that were previously on the right, which consists of, these points here and these points here were previously separate, now they're together. And we're going to use that same technique for computing ranks. We already know the rank of the points on the left, the true rank, because they can't dominate any of the points that are to the right. But when we take these 2 points on the right, we need to check if there are any points in the new merged set that are beneath it. And in this case, there was one. And you can see that we've represented that by saying we have the initial rank of 1, which came from this point because those two were together. And we've added an additional one because when we projected these points together and sorted them by y value, we discovered that this point is also beneath it in y value. And so that gives this guy a total rank of 2 so far in this local scope. Likewise, we've done the same thing over here, but it's less interesting because nothing new needed to be represented. And finally, we merge back to our final set. And you can see that this is now represented just as 2 instead of 1 plus 1 because nothing new needed to be merged into it because it's actually on the left side for the final merge. But this point's on the right side and it got updated because it's actually above these 2 points. And in this way, you can see how we might solve a 2-dimensional problem by using 1-dimensional base cases with multidimensional divide and conquer. Now that we've sort of established the idea of multidimensional divide and conquer, and we've looked at a practical application, that application being the all points ECDF problem, in 1 and 2 dimensions, where we really only used the multidimensional divide and conquer strategy a bit in the 2-dimensional problem. Let's think about what it would take to extend this to k dimensions, which is really the interesting part, right? And it's not too much new information to think about or too new of an idea once you've seen that 2-dimensional example. The first question that probably comes to mind is, okay, so we used a line to divide in 2 dimensions, to divide up that 2-dimensional space, and perhaps we could use a plane in 3 dimensions, but what will we use in k dimensions? And the answer is simply a multidimensional plane on 1 less dimension than the problem size that you're working with. And that allows you to maintain problems of size k, well, problems of dimensionality k, I'll say, while still getting sizes of half the points of the original problem. And in that way, you can just continue dividing down your problem until the sizes get small enough to where you can perform those successive projections and just progressively take away 1 dimension at a time until you've reduced down to the base case type problems in 1 and 2 dimensions that we've already worked through. So what kind of runtimes can you expect from such an algorithm, such an implementation? And the author has provided arguments for a big O runtime of n times log to the power of k minus 1 times n. And there's actually an interesting concept called pre-sorting, which is used to reduce from log to the power of k times n to, that k minus 1 power, and sort of divide out 1 power of k from that logarithm. And that actually, the general idea of that, although I won't go into it in detail right now, is that each time you need to perform those merges and those projections, you need to sort the data on one of its dimensions in order to compare it and establish rank in that dimension, so to speak. If you pre-sort and carefully which would basically be sorting everything beforehand and carefully maintaining that sorting in a given dimension, then you don't have to perform that sort every time you need it. And that's the general idea of how we can reduce the runtime by that factor of log to the power of k. So that concludes my presentation about multidimensional divide and conquer. It's a very interesting idea, and hopefully the one in-depth example of the ECDF all points problems really gives you a grasp of its usage and how it is specific enough to actually provide a pretty specific technique for solving a problem while still being general enough to apply to the other problems. Unfortunately, I haven't gotten to those other problems here, um, but it certainly does, and that can be found in the multidimensional divide and conquer paper if you're curious about those other use cases. Thank you for listening.